Generic face image quality assessment technology is crucial for both camera applications and social media platforms. Its goal is to take a facial image and let the network predict the mean opinion score for the image. Our IQA framework consists of three networks: the Cvpr network, the landmark detection network, and the degradation extraction network. In our Cvpr network, our model uses a vision transformer to extract features. These features are called IQA features, which are later combined with the degradation representation. The combined features are fed into the regional confidence head and the regional quality heads. The regional quality head predicts the quality score of each region. The regional confidence head predicts the importance or weight of each region for the final quality score. The outputs of these two heads are combined through a weighted sum to obtain the final quality score. Meanwhile, the degradation extraction module extracts the degradation representation. According to previous literature, information about degradation is crucial for image quality assessment. A reliable degradation representation can provide good guidance for IQA. Therefore, we use cross-attention in the transformer decoder to combine the degradation representation with the IQA features. Specifically, based on cross-attention, we use the IQA features as keys and values, and the degradation representation as the query, making our IQA features degradation aware. At the same time, we predict the landmarks of the input image and use positional encoding to encode these coordinates, enhancing the network's representational capacity. Subsequently, this encoded information, along with the IQA features, is fed into the regional confidence branch to generate a confidence map. The question is, how can we train a sufficiently accurate degradation extraction module? A naive idea is to add synthetic degradation to high-quality facial images and use these labeled examples to optimize the network. However, because the degradation is synthetic, it cannot generalize to real-world scenarios. The patch-based solution assumes that degradation across image patches is uniform. Patches from the same image are considered positive samples, while patches from different images are considered negative samples. These patches are encoded into degradation representations, used for querying positive and negative samples. Then, a contrastive loss is used to optimize the degradation extraction module. However, due to various factors such as lighting, local motion, and defocus, the assumption that degradation is uniform across the entire image is often inaccurate. Furthermore, in real-world scenarios, like a moving face against a static background, only certain patches may experience motion blur. These issues lead to suboptimal and inconsistent results in degradation learning. To address this issue, we propose dual-set degradation representation learning to train the degradation extraction module. In DSL, we design two sets of image collections, Set S and Set R. Set S includes images derived from high-quality facial images with synthetic degradations such as noise, blur, and low lighting. This set acts as a controlled environment, allowing us to explore diverse degradations under constant content conditions. Set R contains images from real facial datasets, each with different content under real-world degradation conditions, reflecting the diversity of real-world degradations. First, each image from both sets is mapped to a degradation representation. Based on these degradation representations, we calculate a soft proximity mapping for each degradation representation. We compute the similarity between each synthetic degradation representation and all representations in the real-world set. Then, we weight and combine these real-world degradation representations based on their similarities to obtain the SPM. Next, we optimize the SPM in Set S using contrastive loss. Specifically, we attract a given degradation representation towards its own SPM, while repelling it from the SPMs of other images. This optimization leverages the characteristic of images in Set S sharing the same content but differing in degradation properties, contrasted with Set R, which varies in both aspects. The degradation extraction module is trained to learn a global degradation representation by attracting the extracted representation to its corresponding SPM and repelling it from others. This approach allows the degradation extraction module to accurately extract degradation representations in real-world images, approximating the synthetic degradations in set S. In DSL process, we introduced a bidirectional learning mechanism that enhances our understanding of degradation by learning in two directions. Specifically, degradations in different images in the real world can be considered as different components. Therefore, we compare real-world degradation representations with synthetic ones. We calculate the similarity between each degradation representation extracted from the real-world set and those in the synthetic set, and compute its SPM using a weighted sum. Then, we apply a similar contrastive loss to these representations. This design strengthens the mutual learning process, ensuring that both sets contribute equally to the understanding of degradation. Thus, this bidirectional learning helps the network gain a more comprehensive understanding of degradation. In our landmark-guided approach, we focus on facial landmarks because they are key to understanding how people perceive image quality. The human eye is particularly sensitive to details in facial features. By identifying and emphasizing these landmarks, our model can more accurately assess image quality. We input this landmark information into our network's regional confidence head to ensure that our assessment prioritizes facial regions most important to human perception. This method allows us to more accurately assess image quality, reflecting the natural way we observe and judge faces. Thank you for your attention. Please read our paper to find out more.